Today we are going to present HyperMesh CFD version 2023. So let's dive into it. So before we get into HyperMesh CFD 2023, let me reiterate the announcement which was made by Lee Christman about the updated products, platforms, and the product name. So now under Altair 1, we have 3 platforms: Altair HyperWorks, which is for design and simulation platform; Altair HPC Works; and Altair RapidMiner. And then to accommodate that, there has been some change into the name. So now HyperWorks is called HyperMesh. HyperWorks NVH is referred as HyperMesh NVH, and HyperWorks CFD is now will be called HyperMesh CFD. So with this name change, let's see today's agenda. Before we get into introduction of HyperMesh CFD 2023 version, let me step back and give you some details about the motivation, about the features which we worked upon. So last year, the top management team, the business development team, and the product development and product management team agreed upon a goal to focus on the automotive CFD solutions and deliver a competitive workflows and solutions for external aerodynamics, fan noise, greenhouse noise, battery cooling, cabin thermal, and underhood thermal. Looking at the requirements for those solutions, as well as the prevailing competition and their workflows, we identified the challenges which we have within our tool sets and offerings. So first challenge is that the tool required to carry out the workflow are scattered across different products. That brings up the challenge that how we can provide the training to the users, and adoption was a pretty big challenge as well. Second was there were limitations into the tools, whether some of the tools which are required to fulfill that solution were missing, or the performance was not up to the mark. And also, since we are relying on different products, the delivery speed of getting out the solution was also slow. So considering these challenges, we defined some tasks for us. So first task was to get a streamlined user interface for the end-to-end workflow. So user does not need to worry about the product. Second, have the complete set of the features required to carry out that workflow. And then third is also focus on the performance and the automation required to efficiently carry out that workflow. So with these expectations and task in the mind, we worked on the product development for last 8 months, and here we are excited to present you HyperMesh CFD 2023, which will provide the end-to-end workflow for aerodynamics and aeroacoustics, as well as the general purpose CFD in a single user interface. So for today's presentation, we will cover 5 segments. First is the solution layer, that how we accommodated all the solution end-to-end workflow by enhancing the user interface by adding a solution layer. We'll also go through enhancements made into the geometry modeling, the case setup, post-processing, and the design exploration. So let's start with solution layer, which is the enhancements in the user interface to get the solution-centric workflow. It's very simple. User installs the user installs the product, and then they launch HyperMesh CFD. When they launch HyperMesh CFD, there will be a startup dialog, which will ask the users to pick up the solution they are interested in. Right now in version 2023, we have exposed aerodynamics and aeroacoustic solution, as well as the general purpose CFD for the internal flow, multi-phase flow, the thermal, and the moving body simulations workflows. Once they pick up the solution, behind the scene, we'll set up all the required modeling environments, as well as the tools which are required to carry out that solution. So user can define like what is the modeling environment they want to work with, and we'll expose the relevant tool sets for that modeling environment. and then they can carry out their simulation. This solution layer enables integration of Altair's vast technologies and provide a single user interface for end-to-end and workflow. So that is a pretty important aspect about this solution layer. That behind the scene, it may be using different tools and technologies provided by different products within the Altair. So before I get into the advantages of the solution layer, let me give you a small demo. So when you install, it's a one single installation, and when you install the product, you will have this icon called HyperMesh CFD. And when you invoke that, when you click on that, it will start up the UI and it will expose this startup dialog. Startup Dialogs has multiple sections. One is the solution picker. So aerodynamics and aerocaustics is for the workflows where if you want to do the external aerodynamic simulations or the fan noise type of simulations. General purpose CFD is for if you are interested in the internal flows, multi-phase flows simulations, or the thermal simulations or the moving body simulations. So you can pick that solution. You pick that solution, you define like what is the default modeling environment which you want to get into, and you can define your startup directory. And then you can say create the session. Based on the selected solution, it will expose the relevant modeling environments as well as the tools required within each of the modeling environments. So user interface wise, it's nothing. It's pretty straightforward. All the file menus, all the edit and views, and all are consistent. Now let me start opening a file. So to demo the process, I'm loading a model which I loaded the geometry. I wrapped that model. So now it's the modeling is the geometric modeling is done. Now the next step for once you are done with the geometry model is to take this model to the setup environment. We have this case setup environment, so you can go through that and do that. So to do that, you just click on this data transfer, you select the parts which you want to take it to the setup environments, and you click on transfer. When you do that, it knows that it has since the current modeling environment is geometry modeling and next is case setup, it will take the data to the case setup environments, and then you can start working on the case setup environments. If you look at the model browser, all the names and all the colors of this model of the model in the data into the modeling environments as well as into the case setup environments are consistent. So this is one aspect. The most important aspect, let's say you made some you did some setup which Raja will go through in detail. So let's say I pick this example and I define the refinement offset layers on this one, and then I come out of it. Now let's say if I go to the modeling environments, I want to work on the variant modeling. So I want to replace a part. So in order to do that, I can go to the modeling environment. I can select that part, and I can, in the modeling environment, I'll say, let's replace this part with something else. So I have this another step file. I'll click on that. I load that, and it will replace. So in the modeling environment, I'm changing this part because I want to work on the variant modeling. Then I can just mesh these parts. So I select the surfaces based on the parts. And define the sizes and say mesh. So now I'm working on the modeling environment, and I want to take this updated parts to this modeling environments. So let me turn it off so the color is right. So now if I want to take this updated part to the setup, I again click on the data transfer. tool, I click on the part, and instead of saying that discard all the data into the setup environment, I can say append and replace the new data, and I click on transfer. So you can see that that part is transferred, and all the definitions which was defined into the case setup persist as it is. So this environment will seamlessly help a user to do the baseline model as well as the variant model where you want to change the parts and names and everything. And once it is done, since the file menus and everything are consistent, one of the biggest aspect is that I can save this as the session file, which is we are calling it as HMCFD, and I can say this is my setup data. So this contains the data for required for the modeling environments as well as the setup environment. So now when you open that file again, you will have both data together in a single session file. So in short, this gives us the advantage of the single user interface with the single modeling, single user interface, single installation, single documentation, and single data set. So with that, let me explicitly go some of the slides. So as we have seen, the solution layer. So let's look at some of the advantages which it provides. So first advantage is it provides the solution delivery is simplified significantly. In order to understand that, let's look at the workflow which we had before. So let's say we are looking into the aerodynamics solution. For that, we have to identify what are the modeling environments that are needed for that solution. And then we need to pan down that what are the products which can help us for that modeling environment. So what are the tools required for that modeling environment? And you have to map it to a product. So to get started, user has to identify all these products, install these products, also get the licensing for each of the product. Not only that, they also needs to understand that how they work with each other even before getting started to the modeling aspect. With this new HyperMesh CFD version 2023, this will be pretty seamless. Solution is integrated that user can directly select the solution within the UI user interface, and all the modeling environments will be set based on the picked solution, and all the tools and data transfer are inbuilt within the tool. So if you want to deliver a solution, this will be much efficient way for the users, and it can scale up, and training will be much easier. And of course, this provides the solutions out of the box. User does not need to think about products. They just think about what is the solution they are interested. And based on the single installation, single licensing, and single documentation, this provides a singleton user experience to the users. Second, let's look at the modeling process. And to understand how it is simplified, let's look at the modeling process, what was before. So before we go through different modeling environments, which is different products. And this is the layout of the XML arrow process. With each of the product transition, we need to identify like what is the data set which I need to transfer from one of the modeling environment, one of the product to the other product. So here from the geometric modeling product, you have to transfer the STL data and take it to the setup, and then you work towards that. Not only that, you have to save multiple data sets for each of these products. So single simulation involves a lot of data exchanges as well as the data sets which needs to be carried out. Same goes for the post-processing, that you have to take different data sets and then you have to use different products to carry out the required post-processing. With HyperMesh CFD 2023 version, now you can do all of those into one UI. So geometry and modeling, once you are in one UI, and once it is done, you can write out the data required for the solver. And once the solver is run, you can take the data from the solver and you can do all the post-processing, signal processing, as well as the report generation into the single UI. So this significantly simplifies the modeling process. Not only that, we just need to save one data set file, which will contain all the data. So along with this, the simplification in the modeling process, this also provides the advantage of the performance. So if you look at the process before, if we have to transfer the export the data from the geometry modeling environment and import into the setup for one of the model, it takes around 400 seconds. Now, with this environments, the same model, if we within this, we can exchange the data in 30 seconds. Not only that, it knows what are the part names and colors and all those needs to be transferred as well in order to provide the singleton user experience. In future releases, we'll be leveraging a common data module, which will make this data transfer and data syncing much more seamless. So that is another big advantage. Third, which is this provides a pathway for the new solutions. So in 2023 version, we added solutions for external aerodynamics and fan noise. In future, we'll be leveraging other offerings within Altair to add more solutions within this user interface as well. So the advantage is that all the contributors will work in parallel towards a common goal. So there will not be duplication, and user does not need to think about which product to use. Based on the solutions, all the required products will be set behind the scene, and user can have a singleton user experience. So the other improvements, as I mentioned, that now we just have one file format, which has all data for geometry modeling, case setup, and everything. So user just needs to manage that. Installation process is single, and licensing as well as single. So it's user does not need to think about which products are required and different licensing structure. Also, we consolidate all the documentation into one. So this will help the users to go through the solution and adopt it pretty quickly. Along with the user interface improvement to make the end-to-end workflow seamless, we also added improvements into capabilities for the completeness of the features for a given solution. So we'll go through that. Enhancements onto the geometry modeling, setup, post, and design exploration. So to start with the geometry modeling, for external aero use case, one of the requirement is to bring this huge vehicle models into the session. Those models can have anywhere between 5,000 parts to 30,000 parts, and loading them takes time, and even managing those huge number of parts is difficult. In order to provide an efficient solution, we came up with a new approach called light modeling. So what it does is that you can bring in this huge data, and you can select that. Okay, I just want to bring in the faceted representation of that model, and then you can work with the rendering, identify what are the required parts, throw away all the unused small parts, and those type of things. Along with that, it also provides you the capability to mesh those parts into the batch mode. If you're not happy with the faceted data, you can mesh those parts into the batch mode without loading the CAD data. And also, you can continue working on this light faceted representation of it. And if you think that, okay, I still need to load some CAD data, you have this options that you can select the part and can say, bring the CAD data for this part. So you can interchange between the CAD representation of the part or the light faceted representation of the part and continue working with that. The advantage this workflow provides is that the import time will be significantly lesser. So the biggest step to get started with the modeling full vehicle is to import this huge model, and importing itself can take 5 to 6 hours. So rather than waiting those 5 to 6 hours, you can choose to load just a faceted representation of the model. So one of the model which we got from the customer, it has around 7,000 parts. So it takes if you load the CAD representation, it takes 320 minutes. If you load the faceted representation, you can load that within 4 minutes. And this way, you will get a pretty big head start, and you can start working previewing the model, identify what are the required parts. And even if you feel that the facets which we brought in from the CAD file is good enough, you can start working on that facet itself. Second is the memory footprint. Because of loading of faceted representation, the memory footprint is significantly reduced, and also the operations required. Operations performed on those light representation will be significantly faster. One of the examples is that if you load this huge CAD data in a faceted representation, it takes 40 seconds to save that file. Versus if you load the CAD representation, the saving time itself can be 5 to 6 minutes. So not only just a rendering perspective, but also loading those data and saving those data. This has pretty significant improvements. We'll go through the demo. I know we have a lot of content, so we decided that we'll put the demos towards once the Q&A is done, so that we can cover all the major points. The second is that we improved CAD wrapping significantly. So typically for the full vehicle model, the current workflow is that they bring in the CAD for the class and the exterior body surfaces to preserve the class surfaces as it is, and then they use the wrapping for the underbody parts because it's faster and automated process. The CAD approach, CAD wrapper is a technology which brings the fidelity of manual CAD stitching and operations, as well as the automation of the traditional wrap. And this eliminates a lot of manual work. So typically, when you manually stitch the surfaces, it takes 3 to 5 days for manually stitching the surfaces and preparing the model. With this CAD wrapper, you can reduce those time to 5 hours. So you can bring in just a light representation of the data, and you can start working on that. And within a day, you can get your model. The advantage is that it keeps the class surfaces as it is, but also it will make sure that everything is watertight, and it will seal all the gaps automatically. It is pretty efficient in terms of memory footprint and the speed. So right now, a full vehicle model, which has around 20,000 parts, we can wrap it under 2 hours, which is quite competitive compared to the commercial tools available. Not only that, this also reduces the learning curve. User does not need to know all the manual geometry editing tools. So that's why they can easily grasp this entire process quickly. We had one of the intern joined us for the summer, and within a couple of weeks, she was able to work on the entire full vehicle model. So this provides the automation for creating a watertight geometry. The next is we added a new tool called Derived Regions, which helps users to create the volumetric refinement zones around the selected parts. So around the mirrors, around the bodies, you can create a body-fitted refinement zones with the user-defined offsets. Another derived region is the projector region. So if you have the car model, you can create this projected the surface to identify the frontal area of the vehicle. So that is another tool which we have added, and also the revolved region. So user can create the MRF region automatically around the fan geometry or around the wheels as well. So those are some of the tools which we added to go through to the end-to-end process. Some other notable improvements, we improved the template manager to support the part-based automation. So now user can select the parts. You can define the groups based on parts by either the metadata of the parts or the names of the parts or the names of the assemblies or the IDs. This will help to create the automation layer for the vehicle modeling. Not only vehicle modeling, but this will also help for the other parts as well. And along with that, we also added the new operation called bulk operation. So user can define various operations and define the templates for that. Some of the other improvements we made on the model organization that you can move selected elements or surfaces to any selected parts if you want the specific requirements at the setup side. And also, FE geometry, the core team made significant improvements in terms of the rendering. So now all the show, hide, isolate on those large models is instant. So those are some of the notable improvements. Next category, I'll cover the design exploration. So we started working on the design exploration to provide the capability for the users that they can morph the shapes of the model and perform the DOE studies. This is available for both AccuSol as well as the UFX, and then we also made the connection to HyperStudy. So let me briefly give you the demo for this. So along with the modeling environment, you can choose to design exploration. So with that, you have this ribbon called morphing. So using this ribbon, you can go through different tool sets and define the volumetric morph zones, or you can do the free morphing as well by picking some of the edges, surfaces, or nodes. And then you can morph using the handles, you can morph the shapes, and then you can save those shapes as well. So I have defined this morph volume, I have split them, and then I have those three shapes. So you can also preview using these shapes that how those morph volumes are defined, and then you can preview that as well. Once it is done, we have added this tool called DOE study. So if you launch that, you can define what is the directory where you want to perform the studies. You can choose your solver, that what is the DOE study is based on the AccuSol or the UltraFluidX. You can define the execution directory. So this is for the UFX. So you can define the execution directory, and the available study types are like shape based, or if you have the CAD parameters, you can perform the CAD parameter based study as well. So here we have the shape based, and you can define the setup template. So if you already have XML file, so you can choose that already defined XML file and the post automation file as well. So if you have that post automation file, the IMG file, you can define that, and you can click on launch. What it does is that it takes all the setup which were there, all the design variables and everything. It launches the HyperStudy with all the settings available. So you can do the import variables, and you will see all the defined shapes and design variables will be brought in, and you can carry out the DOE studies as well. We can do more demo on this as well later on. So with this, let me hand over to Raja, who can continue the step towards the setup.
All right, thank you, Harsh. So let's head to the simulation case setup environment. So once you are done with your geometry and modeling, you would take your data transfer tool and bring the data to the case setup environment. And this case setup is going to be specific to the external aero workflow. So you'll be using the UltraFluidX solver in the background. So what we've done, and this is the biggest change that you'll notice in HyperMesh CFD, is that virtual wind tunnel has been completely and seamlessly integrated into HyperMesh CFD. So users of VWG will now be using HyperMesh CFD going forward, and those who are familiar with HyperWorks CFD will see that there's a new capability that's been added in. And this environment is a dedicated UI for the ultrafluidic solver. It was designed to be easy to use for both beginners and experts. And we now cater to the vehicle aerodynamics and the fan noise simulation scenarios. The UI also incorporates a lot of the solver's best practices right in the UI, and I'll give you a few examples of how that works. Under the hood, it leverages Inspire's geometry engine, and you have Polynobes tools that you can access for advanced workflows. Automation is enabled by the Python API, and that also enables batch mode. So you can run the entire UI using a single script without launching the UI. And the narrow vertical focus that we have also enables optimization like STL representation, where we were able to take the database and optimize it just for the STL models that we primarily use for UFX. And that resulted in a 2 to 3x faster I/O. So we have read-write speeds that were dramatically faster. At the same time, the memory utilization also came down by more than a factor of 2. And this is rehashed for folks that have used virtual wind tunnel, or if you haven't, once you get into the case setup environment, you'll work your way from the left to the right. So you start with bringing your models in as STL files. Once you've imported the model, you organize these parts in the model browser, and you create your wind tunnel. You'll see that the wind tunnel was automatically sized for the car that you brought in based on best practices. Once you've done that, you identify which parts exist in the car. This is essentially your boundary conditions. So you'll identify your wheels, fans, and heat exchanger zones. Once you're done with that, you pass mesh refinement zoned hints to the solver because UltraFluidX does not need a volume mesh. You pass the hints to the solver, and the solver will do the meshing based on these mesh refinement zones. And the next step would be the outputs that you want to collect. So these will be in the form of surface or volume probes, surface outputs, monitoring surface outputs, section cuts. And finally, you have a way to run the solver from within the UI. So, and this works if you're on a Linux machine with a supported GPU. If you're on Windows, you would export the files to an STL and an XML file, which you move to a Linux machine with the right GPUs, run the simulation there, and you can bring it back. Once you're done with the solver run and you have results, right in this environment, you can hit the visualize button, and that will take you to the post environment. Let me give you a couple of examples of what the smart UI and how we incorporate the solver's best practices. In this case, I'm trying to create a turbulence generation zone. What I do is I hit the turbulence icon, and I would click a part where I want to create turbulence. And what it does is it automatically creates a box around that part, and that's automatically sized. And here you see two entities. You have a blue plane and you have a box. The blue plane is where the turbulent eddies are created to generate turbulence, and the box behind it is the mesh refinement zone. And this was automatically computed for you. There are a few other advanced parameters that you see on the right, like what is the plane offset, what are the eddy sizes, and how many eddies are created on this plane. All of those are automatically set for you based on the solver's best practices. So if you adjust one of the parameters, like the refinement level, you'll see that the rest of parameters are automatically scaled based on the solver's recommended best practices. Another example is the fan guide panel workflow that we introduced recently. Here we ask simple questions like, what is a fan? So once you identify a fan, the center and axis of rotation are automatically computed. The next information that we need from the user is how fast is it spinning. So you provide the RPM of the fan. And finally, you decide what fidelity you want to solve this problem in. Do you want it to be just a wall boundary condition, or do you want an overset mesh? And when you select something like an overset mesh, you will see that a volume that wraps around this fan was automatically created for you. And in addition, you have parameters like what is the distance between that the overset volume and the fan's geometry. And in addition to that, you also have an automatic mesh refinement zone, and the interface can also be refined by the solver. So a lot of these parameters were automatically computed by the user just selecting which part to assign as a fan, and you just tell us what speed it has to be spun at. The rest is taken care. And if you are an advanced user and want to go ahead and edit, you can go ahead and edit all of these properties. And finally, let me walk you through our Python-based automation. Let me draw your attention to the video running over here. So a script was basically invoked, and that script brings in the car model. It creates a wind tunnel for you. And now it's going through the identified parts. And you'll see the wheels, the fan, and the heat exchanger in the front get highlighted. And once that is done, you have the belts that were configured, and you have refinement zones that come up. Some are box-based and some are custom fitted. And then now you see the outputs. So you have the probes, volume probes, surface probes, section cuts. And finally, the entire setup is being exported to an STL and an XML file, and it's ready to run. So you'd hit the play button to run the solver. And if you hit the visualize button, you would bring up the solution in the post environment. And let's take a look at the left side of the screen. And this is a preview of what the script looks like. You bring in a few Python modules. And to illustrate that, this can be run in both the interactive mode, as you see on the right, or it can be run in batch mode. The script here creates a new model, brings in an STL file, creates a tunnel, and you can go edit all the properties of the tunnel here. So anything that you can do in the UI has an equivalent Python command. So you can set up your 1:1 script once you've decided what you want to do in the UI. And once you've created all your parameters, you can save the model to a database file, or you can export the simulation. That gives you your STL and XML files for the UFX solver. And if you have the right operating system and the GPU, you can also run the solver from within your Python script. At this point, I'll hand off to Mike, who will walk you through the post-processing.
Okay, hey everyone. So thanks for joining us. So I'll be going through the capability enhancements with respect to post-processing within our single integrated workflow. So first off, I just want to give a brief overview of post-processing for CFD within HyperMesh CFD. So we do support all the Altair CFD solvers within our ecosystem. So that includes AccuSolve, UltraFluidX, NanoFluidX, Electroflow, Inspire CFD, and we are also adding support for EDEM. So we will have kind of a wide array of support. We also support generic Insight case files. We have designed the back end of Post to support very large data sets on the order of 1 billion cells, and that's to support the aeroacoustics workflow from UltraFluidX primarily, but each of the solvers can take advantage of that back end. We've tried to put a significant amount of focus on what I would consider more advanced post-processing capabilities, more for engineering analysis in the previous couple of releases, including 2023. So we have made sure that we're able to compute derived computational fields for engineers that need to understand, say, coefficients within their data sets or derivatives in space and time. So that is capable within the tool set via our calculate menu. And we actually have shipped some of those formula so that users can just load them up and not rely solely on the scalar outputs directly from the solvers. We can take data sets and manipulate them in many different ways. So sometimes extracting your data along a 2D line or a surface or from, say, point probes is needed. And at the same time, aggregating that data onto a surface for integration to interpret those large data sets might be required. So we do support many of those workflows. And yeah, those have been released over the previous years as well as 2023. So for this release, one of the features we did focus heavily on was acoustic analysis for CAA, noise prediction and identification. So I will be going into a little bit of details about the general signal processing and what we introduced there. And then lastly, for the automation aspect, we do include a report tool that leverages the HPL backend to create reports and images or animations so that users can very easily create a professional and consistent looking report for multiple data sets without having to enter the user interface. And then I should mention all of this is developed in tandem by Altair and Kitware Incorporated. And that does help us leverage the sort of industry approved functionalities with the ParaView backend. So the first feature I want to talk about in terms of enhancements is general signal processing. So this is a tool that we've added to hopefully keep our users within HyperMesh CFD and not have to move within multiple GUIs to perform computational aeroacoustics. So the basic premise of the workflow is that an engineer will take one of their output streams, whether that's a CSV file or a surface data in the format of H3D. They'll bring that data into HyperMesh CFD post, and the data would consist of pressure as a function of time, either in the probe or on the surface. So we will use an algorithm in the backend to compute that sound pressure level in the frequency domain. And that will be done again, either on the probe level or on the surface level. So what we do is essentially take that raw pressure signal, a series of FFT parameters, and then the weighting and scaling parameters. We bring those into the batch process and send all that data into a new file format that we've created with extension GSP-H5. So this, as the name indicates, is an H5 file, and that file will contain all of your input source, but in a transposed way, so it's very easily accessible, as well as the topology coordinate and the associated cell data, and then also the output set. So depending on what the user requests, if they request one or both, we would support storing the hydrodynamic dB map and then also the band filtered animation so that a user can load that data back into post and basically view those results on, in this case, like I'm showing on the vehicle windscreen and side glass. So we needed to create this to essentially maintain users in that integrated workflow. So our legacy tool set with NVH Director required users to go to a different tool and was not quite as performant of what we've done in this release. So while that tool set provided some advanced capabilities and actually made it easier for us to implement because we could leverage that reference, we were able to rewrite that formulation and save a significant amount of processing time compared to the raw H3D read. And then if user actually needs to reprocess this data set, they can load up that H5 file and recompute any of the acoustic fields that they might need. And we saw when you do that, you go from a processing time of approximately 9 minutes with reading the raw H3D file down to about 2 minutes with reprocessing through the H5 file. So just to kind of further explain why we did this, I tried to recreate one of the slides that Harsh showed earlier that essentially shows our entire workflow. So here we have two different blocks just shown horizontally, where at first we have more of the scattered workflow or the legacy workflow, and then below the orange line we have the end-to-end workflow. So you can see the blocks are color-coded by the legacy tool that was required to perform that step. So in the first scattered workflow diagram, we have our pre-processing steps that were a combination of HyperMesh or HyperWorks and then VWT. We would send that information to the solver deck, and after the solver was completed, we had to perform a couple of post-processing steps just to create the set of files that NVH Director could utilize. And NVH Director did utilize the HyperWorks backend as well as Compose to process data. So that step did require a different set of tools. And then if the user needed to do just their standard flow visualization, they had to use a second post-processing tool. But with the new integrated end-to-end workflow, we now have those steps essentially contained within one UI and the solver. So we're able to do all of our pre-processing, including CAD manipulation and discrete meshing, as well as the VWT setup, and then send that to the solver for execution. The solver exports directly an H3D file now, and that H3D file is able to be read in by the signal processing tool, as well as the standard flow visualization tool and the report mechanism. So this image here shows our CX1 model, where we have a slice plane showing the time average of velocity, as well as the sound pressure level on the side glass to represent the acoustics on the vehicle. So we have added some advancements to HyperMesh CFD report. So this is a batch automation process to create collections of images and animations, and then a complete summary of a CFD simulation. So all of this is accessible via a user modifiable text file. So it does rely on having some simple command blocks for each of the representations that a user might be interested in, as well as a view definition so that the user can set up where they want to be viewing their scene from. With that information, and then just a quick reference to how that image should be created, whether it's just a static image or, like I'm showing in this animation here, a spatial dependent image, or also a time dependent set of images. We can recreate a report in a nice, repeatable and seamless way. And then we've also integrated the signal processing tool within that report tool. So you, like this plot shows in the center, you're able to compute a FFT of a point probe to kind of interrogate your acoustic analysis from your point probe files, and similarly for your surface dB maps. So we did actually increase performance quite a bit. So just in comparison, for a relatively small model, the legacy tool set that relied on AccuFieldView to create a report took approximately 5 minutes to run, whereas when we're using HyperMesh CFD report with the HPL backend, we've reduced that turnaround time for a report to approximately 1 minute. So now I just want to cover a few of the more general purpose features that are within HyperMesh CFD report. So for 2023, we added the ability to create volume rendering. So this is defined at the part level. It's a volume property. So this is accessed by going into your part browser, right-clicking on a given part that you want to render the volume for, hitting edit. And with this pipeline, we automatically create a Cartesian grid in the background to sample the unstructured mesh to. So as a part of that pipeline, we require users to set a number of sampling dimensions. So just XYZ sampling dimensions. And with that, the backend goes and resamples the unstructured mesh onto a regular grid of that dimension. So this is done to reduce processing time, and anyone who's familiar with trying to render volumes, they can be quite heavy. So this does make it feel much more interactive and smoother and faster. Once we do that, we apply an opaque map based on the scalar function. So this essentially allows the users to highlight certain values within their scalar field for trying to understand, say, recirculation zones or high pressure regions within the flow. So as I mentioned, this is accessed from the part level. So it is a volume property, which essentially we thought would be a good place to define at the part level. So you see here, once you enter the right-click menu, you bring up the display properties for the volume. You can set, say, your surface display properties that contain that volume. And then we have now the sampled volume tab on the far right to define any of the volume rendering capabilities. So once you define those, you're also able to define your opaque map. So here's showing where you're entering into the legend display properties. If you left click on the hamburger menu next to the scalar based opacity, we enter into the far right context where we're able to define your transfer function that sets up how transparent a given scalar value is. And we do have a couple helper functions here. The opacity type being normalized as the primary. So this will allow for whatever the user sets up in their initial display properties in terms of the min and max of the field to normalize those values for the transfer function. So it just makes it a little bit easier to work as a percent of that scalar field, and then define the opacity again from 0 to 1. If the user wants to do absolute values, they can set that again at this level. So our primary use case for defining this in HPL was for nanofluid X, so that they could take advantage of it in the SimLab product. So here's an example of a water draining model where we're setting up the volume rendering within the full volume to color against the volume fraction of air and water. So in this case, we just set all of the air within the volume to be transparent, and then all of the water to be some value of the scalar field. So it sort of highlights the edges of the free surface, and I think it makes a pretty nice representation of the water flowing down this flat plate. So one other feature we've added that was a request at the customers, and we had in our legacy tool set, was the ability to create traveling vectors. So this is essentially just creating a set of streamlines within a flow field for a steady state time step, and then drawing vector glyphs along those streamlines, but having the ability to animate those vectors as they would move along the streamline. So this is an example from an AccuSolve data set for internal flow within an exhaust manifold. So in this case, we're showing two different animations where we created surface streamlines from the wall shear stress vector, and then draw those vector glyphs on there, and then color them by temperature on the left. And then similarly for volume vectors, we can create streamlines within the full 3D volume using the velocity vector, and then color them by velocity magnitude. So this is really essentially the same set of backend technology that's working and used in two different ways. So users can access this from either the surface streamlines or the streamlines tab within Post. One other enhancement we added for 2023 was the ability to compute uniformity index. So looking at this same case, a user might be interested in computing the uniformity index at a location or on a derived surface that's different than what they had from the direct solver output. So here I'm showing an example of where you might compute the uniformity of temperature at some slice plane, some arbitrary slice plane within the flow field, or at a boundary group here showing the outlet, but that information wouldn't be computed by the solver. Now it is a post-processing operation if the user would like to create that, say, random slice plane, or use a scalar that either they've defined or is some other scalar that's not available as a direct solver output. One other thing that does help to, again, sort of point out certain things within the flow field that an engineer might be focused on or interested in is the ability to limit the vortex cores by thresholding them. So in this case, the image on the left shows our just raw calculation for vortex core identification. And we can see that we do highlight the vortices, but there's some secondary recirculations and smaller vortex cores that might not be as of great of interest to the engineer. So with the thresholding functionality, we're able to threshold out all of those smaller length vortex cores, and we provide a slider bar to do that. And this does give a nice kind of clean output for what the vortex cores look like, which can help for downstream operations like seeding those predominant vortices for the creation of streamlines. So one option that, and really one thing that we've been trying to work on is the ability to process our data sets faster. So we want to be as performant as some of the legacy tools. So one thing that our tool did in the background, users didn't necessarily know, was automatically compute the normals on a surface. So we found that was taking up a fair amount of time for certain processing operations, like sweeping through a transient data set. So with 2023, we added the ability at the reader option level to display smooth geometry So if we have display smooth geometry on, it will compute the normals on all the surfaces within a model, or conversely, if it's off, we will not compute those normals. And when we turn those normal computations off, we did find we had a fairly significant savings from our transient sweep times and model load times. So we're still working out, I'd say, a nice swath of tests here, but based on the few models I've tested and timed, we're seeing between 20 and 30% savings by turning off the normals computation for a given model data set. So this is a continued area of improvement for us. So with this release, we've also optimized how we read and interpret H3D files. So specific to the H3D reader, we are saving more time in comparison to previous releases, as well as the other direct readers or Insight case files. So this is going to be a continued area of focus for us in the future. So I just wanted to make a quick demo and show the report tool one more time. So again, with this tool, you are able to create a standard set of post-processing outputs from a given CFD database. So essentially, the user needs to go and set up whatever context or content they need in their scene, a series of camera views, whether they're the standard views or custom views, and then whatever sort of design review they're interested in seeing. So if it's just a static image or a dynamic temporal animation or dynamic spatial animation, those all go into a single input file that has the extension .img. We take that, send it to our batch automation script, and we have Python drive the backend of HyperMesh CFD post. So user does not see the GUI in this set of interactions. They essentially just see the process running, and it will return a set of images and animations in an output folder, as well as a compiled PowerPoint of all those results. So this is something where we targeted for UltraFluidX at first to help in their release processing and their release testing, so that they could utilize the old set of .img files, run these reports, and then get an understanding of how the tool is performing between releases. But we have sort of leveraged that initial premise to allow for a more general usage. So we can support all of the same files that we do within the standard GUI, and run all the representations that are available for the most part within the user interface. So this supports AccuSolve data, UltraFluidX data, Nano, and we are able to create animations very easily and repeatably with this. And of course, the static images and the compiled report would come out of that as well. Okay, so that's essentially it for all of the capability enhancements. So I just wanted to take 1 or 2 minutes to talk about our future development. So the solution layer approach does leverage the sort of legacy tool sets that users are familiar with by product name. So Inspire and HyperWorks CFD, as Harsh mentioned before. But in the future, we want to try and integrate other tool sets. So the AccuSolve workflow, of course, has been developed significantly in SimLab in the past few releases. And this solution layer does allow for us to take that into account if that's a direction that the company is ready to go in. So we can expand that solution layer to include whichever tools are predominant and most useful to our CFD engineers within the HyperMesh CFD environment. So in order to do that, we need to continue to leverage the common data model and actually build that out in a full-fledged capability to seamlessly transfer information between each step of the process. And that might include exchanging additional geometry information, metadata, and various properties from that geometry, and then having the ability to sync that data across each of the modeling environments. So in terms of capabilities, we do need a little bit of enhancement to our geometric modeling for external aero use cases to hopefully allow users to very quickly take in very large CAD models and boil them down to just the Class A surfaces and the pieces of information within that CAD that are required for aerodynamic analysis. We have a bit of AI and machine learning within the toolset now, but we need to continue to leverage that for design exploration and the DOEs. There's a lot of great work going on with remote job submission within the company as a whole. So CFD is really primed to utilize that set of tools as it's developed. So we're going to be working with the teams within the company to implement all the job submission so that a user can essentially run the user interface on their client and then very seamlessly submit jobs out to a remote hardware GPU, for instance, for UltraFluidX, and then easily take back certain portions of information in terms of post-processing so that they can interpret those results without having to move around terabytes of data files. In terms of post-processing, we are continuing to work with the HPL team and focus on each of the verticals that we're targeting within the company. So one of the first things we're doing is looking to get all the capabilities for discrete element modeling into HyperMesh Post, maybe not all, but at least a portion of them, so that we can allow for the reading of DEM files, and then again, focus on the vertical solutions that we're trying to offer now as a company. Lastly, just the unification of solver data is something that we're looking to continue to move towards in the future with HPL. So that's essentially it for our report. So just in summary, our new solution layer does provide a singleton user experience, merging old products into a solution-centric user interface for end-to-end workflows. It does provide a fairly complete set of modeling capabilities for external aero and fan noise. And then we're continuing to support our general purpose usage with AccuSolve. We really found, just surveying, that we are competitive in terms of performance for handling very large and complex modeling. So we want to continue to drive this and present ourselves as really the leading tool set for handling aerodynamics and fan noise. The design exploration and automation environment are really starting to take off. We want to make sure that engineers can perform a job, but then perform that job repeatedly, right? Do it again and learn something from it. Help it drive the design. So with that, I think we can move to the Q&A.